Example 7.1. In a double slit experiment, the distance between slits is 5 millimeters and the slits are 1 meter from the screen. Two interference patterns can be seen on the screen, one due to light of wavelength 480 nanometers, which is blue, and the other due to light of wavelength 600 nanometers, which is orange. A. Is the small angle approximation valid in this situation? B. What is the separation on the screen between the third order bright fringe of the 400 nanometer light and the third order dark fringe of 600 nanometer light? Sketch the situation. So let's deal with those first. A. Is the small angle approximation valid? So the way we typically check this is that we compare two numbers. So we want to compare D, which is the slit separation, versus big D, which is the screen distance. So when you compare them, what you're really seeing here is that if you look at the slits, you are comparing the middle distance. So now let's say that this is the screen right here. Okay, so if this is the screen, we're going to say here is that the screen here is a distance big D. So in this situation, we know that this is D here. Now, if I look at the slit separation, what you're really seeing here is that we're comparing this distance, little d, to big D. So the general rule of thumb here is that if D is much, much smaller than big D, and in this situation, we're saying that they're 5 millimeters apart. So this would be 0.005 meters versus 1.0 meters. You could see here that it's definitely much smaller than 1 meters. So when that is the case, we can use the approximation sine of theta being equal to tan of theta, which is then theta, and that's useful for our situation. So now what I want to do here is that I want to move on to B here, and the first thing I'm going to do here is that I'm going to sketch our situation. So I'm going to sketch our situation to visualize the interference. So let's go look at that thing. So for starters here, we know that we have incident light. So let's say this is our incident light coming in. And this incident light is a longer wavelength. And so this light, as it comes in, this has a wavelength of 600 nanometers, and that's orange light. Now, when I look at the blue light, that has a shorter wavelength. So I'm going to draw waves that are shorter in wavelength. And these waves have 480 nanometer light. So that's our incident light. So now that what we're going to see here is that we're going to see interference as it goes through the slit here. So if I look at my slit, I'm going to say that here's my slit opening. And they're going to impinge on this slit, two slits, and then over here, I'm going to have my screen. So now that I have that kind of set up here, you're going to see here is that this is my central line. So everything is going to be measured relative to this line right here. And so I know that this distance from here to here, that distance right there is D, which is 5 millimeters. This distance from here to here is big D, which is 1 meter away. And you could see here is that in right here, you could see that this is my screen. And then here's my slits. And then here's the incident light coming in. So if I look at my blue light, so I have my blue light, and that is 480 nanometers. But I should immediately write this in terms of meters, because we want everything to be in meters. So that's 10 to the negative 9 meters, and this is my wavelength of the 480 nanometer light. And if I look at my orange light, of course, that's 600 nanometers, or 600 times 10 to the negative 9 meters for that wavelength. So now that I have that, we're then going to go and we're going to do the following thing. So we are asked to determine the locations of, the first one is we want the third order right fringe of 480 nanometer light. Now, because this is constructive, it's bright, this implies here is that if I look at MC, third order means what? 0, 1, 2, 3. So we're talking about that this one right here is the third order. That's the third order bright fringe. Now, the next thing that we're looking at is we're going to look at the third order dark fringe. Now, we have to be careful with the language here now. And this is of the 600 nanometer light. Now note, everything is measured from here. So we measure all fringes from MC equal to 0. So in this case, the third one is really the third bright fringe. But this is not the case here, because when you have MD, it turns out that the first dark fringe that you see is actually at 0, which is not at the center. So if you go 1, 2, this tells us right here that this guy right here, this is the third order, or the third fringe that you see here. So now let's look at our pictures here again. So I'm going to redraw our situation of the with this in mind here, so we get the right picture. So I'm going to redraw the interference pattern. Of 400 and 600 nanometer light. Now what I'm going to do here in this situation is that I'm going to think about this by drawing this on 2 different screens, but they're really right on top of each other. So what I'm going to do here is that I'm going to say, I'm going to come in and I'm going to draw a straight line like this. Then I'm going to come back with my eraser and I'm going to write, and I'm going to make 2 openings here. And there's my screen distance right there. So now that's my 2 slits right there. So then I'm going to draw 2 slits, and they're going to look like this. I mean, 2 screens. Here's going to be the screen right here. And then I'm going to draw a second screen. But note that these 2 screens are really the same screen. I'm only doing this to show that the patterns for both. So these are the same screens. So now, here I go. So now what I need here is that I need my central line, which I'll draw right here. So everything has to be measured from here. Okay, everything is measured from here. So now here I go. I have blue light coming in. Okay, so here's my blue light. It has a short wavelength. And this is my 480 nanometer light. So what am I doing here? So if I'm looking at the bright, note that I see a central bright spot right here. That's MC equal to 0. And then what I'm seeing is that I'm going to get a first order bright fringe. That's the first. Then I'm going to get the second here. And then I'm going to get the third right here. So in between here are the minimas, or the dark fringes. So when I'm looking at this, this is really what? This is 0, 1, 2, 3. So this light is now going to produce something like this. So that means the distance from here to here, that's going to be delta Y3 of the bright fringe. Now, the orange, they're going to produce farther apart fringes here. So what we need to do is that we need to count the dark ones here. So let's look at that. So when I look at the central fringe, Here's the orange central fringe. But these guys are farther separated apart. And so when I look at my darks, I mean, I should probably make these guys a little bit wider. So if I now look at my dark fringes, they're right in here. And so when I look at these guys, what you're seeing here is that for my dark fringes, look what I see. This is 0, 1, 2. So if I look at this distance right here, right, the distance from here to there, this is delta y3, but that's of the dark. So even though I didn't draw it earlier, this is my orange light coming in, and their wavelength is farther apart. And this is our 600 nanometer light. So now our goal here is that what we want to do here is that we want to calculate. So we want to calculate the difference, where I'm going to say that this is delta y. And what I'm saying here is that because the orange light is more spread out, that then it should be delta y third of the dark minus delta y3 of the bright. That's what we're trying to calculate right there. That's the difference. So now, using the small angle approximation relationship, we can write these down. So I know that that these distances now read like this. Maybe I could put it on this side. So the first one has to do with the dark. So it should be MD plus 1/2, the wavelength of 600 divided into little d times big D. And then I have the constructive interference, which should be MC lambda 480 divided by little d times big D. And I'm going to subtract these. So now you could see what's common to these. Big D and little d are the same. So now I can rewrite this to look something like this. I can write this as MD plus 1/2 times wavelength 600. And then this guy's going to be MC lambda 480. And so if I look at that, what I've done here is that I've now separated out big D times little d. So now let's go put in our numbers. Okay, so if I put in our numbers, they look something like this. We know that MD for the third dark fringe is 2, and MC for the third bright fringe is 3. So if I now start putting in my numbers, I'm going to do this here. It's going to be 2 plus 1/2. Now look what I'm doing, that I don't keep it in nanometers. It's got to be in meters. Minus 3 times 480 times 10 to the negative 9 meters. And then I'm going to multiply that by the quantity 5 times 10 to the minus 3 meters into 1.0 meters. And when I compute this number, I get the following value. I get 12 times 10 to the minus 6 meters, which is also 12 microns. And that's going to be our separation right there. So now the question goes like this. Do the 800 and 600 nanometer waves interfere with each other on the screen? So now to answer this question, so do the 480 and 600 nanometer waves interfere with each other? And the answer is no. They have different frequencies / wavelengths that will only interfere for the 3/5 of times. There is no sustained interference. That your eye will see.